Okay, so we're going to continue now with more on conditional probability. Conditional probability, like I said, one of the most important and in-depth and just recurring topics. So it's something that warrants a lot of attention. And I just want to, so I'm going to do, we're going to illustrate a particular type of a guessing game. But just for review, to recap kind of where we are so far, we have a probability measure P on omega. The conditional probability of B given A I'll write it as A given B is defined by probability of A given B. So that's how we write it. Probability of A intersect B divided by the probability of A, provided that the probability of A is positive. Otherwise, we can define it to be whatever we want. We have the law of cases. So what is that? If C1, C2, if we have a partition of some set C in omega, then the probability of A given C, we can express by decomposing over each of the cases CI, probability of A given CI times the probability of CI given C for each event. We have the multiplication rule. Well, let me do it with multiplication, but let me give the law of total probability, which is a special case of the law of cases. In this case, we're partitioning the entire sample space. Then we can calculate the probability of A by decomposing over all of the cases. Probability of A given CI times probability of CI, very powerful. And then finally, the multiplication rule. Which we get in the case of two events just by rearranging the definition of conditional probability up here. And in general, for multiple events, product of AJ given the intersection. This is where, again, we define the intersection from one to 0 as the entire space. How do we prove this? Proof by induction. Right, so it's already true for this for the case of two events. And so let's assume it's true. That's the base case. So base case, it's true by definition here. So then we assume true for n. And then for n plus 1, we have to prove that it's true for n plus 1 events. Now, n plus 1, that's going to be an plus 1 intersect the intersection j equals 1 to n. J equals 1 to n of aj. Apply the base case to this. It's probably of an plus 1 given j equals 1 to n aj times probability of this intersection. Apply the case of n to this, and what we left with is exactly what we asked for. This is the base case. And then this is by assumption. We can fold this first piece into the product by adding, by now taking the product up to n plus 1. And if we do that, we get what we need. All right, so now let's do a guessing game. Let's first consider a deck of cards. So we have a deck of 4 cards. Ace, king, queen, jack. Cards are shuffled and they're laid face down. So cards are shuffled. And laid face down. And they're going to be turned over one by one. So before each card is turned over, you're going to predict either that the next card is an ace, and if you're right, you win. If you're wrong, you lose. Or that the next card is not an ace. And if it is an ace, then you lose. Otherwise, you're going to continue. Okay. And we're trying to analyze this game. So question is, what's your optimal strategy to win this game, and what is your best chance to win? Okay. So as a generalization of this, and we're actually going to do the general analysis, is that we would suppose there are n cards, arbitrary number of cards, and we have with one special card call it star, and we win if you predict where star is. Okay. And so the question is, what should be the strategy? What strategy gives us the best chance to win? And so let's think about some possible strategies. One strategy would be, I'm going to always just predict that the first card is an ace, or that the first card is the special card. So some possibilities. So possibility number one, always predict that the first card is special. What's the probability I win in that case? Well, I'm going to win if the first card is special. There's n cards. So assuming the cards are well shuffled, chance of me winning 1 in n. Okay. Okay. Now, what if I said I'm going to always predict that the last card is special? Well, the idea is if I can get all the way to the last card, I guarantee that I'm going to win. Right? So I'm guaranteed to win because I'll know that that's the special card. Okay, but so there's some logic there, but what's the problem? The problem is it's hard to get to the last card, right? If the special card comes up before then, I'm never going to get to that point. So what's the chance that I get to that point, right? Well, what's the chance that the last card is special? Use exchangeability, right? We're drawing without replacement. We're assuming everything is equally likely, so we can think, well, the probability that the last card is special is actually the same as the first card being special. So probably that we win in this case, 1 over n. My claim is that probability that we win in this game is 1 over n regardless of strategy. So it doesn't matter what we do, how we try to do it. Doesn't matter how fancy or how complex we get. Our chance of winning is always 1 over n. Now, given that there's a lot of different strategies we could imagine using, it's a little bit challenging to think how we might actually go about this. Okay. Huh? How are we going to do it? Well, this is a case where we can apply induction. We can apply induction and use what we know about exchangeability and conditional probability and the law of cases. So we're going to do a proof by induction. What does a proof by induction entail? It entails a base case, an assumption, and then a proof that we induct on n, the induction step. So the base case is the case that n is equal to 1. In the case that n equals 1, there's only one card in the deck and it's special. So we would just predict that that is the special card. I guess you could imagine that we could predict that the special card that the next card is not special. In the case of one card, we would obviously lose in that case. So we probably need to modify this if we're being very pedantic, that it's regardless of strategy, where the only where we always assume that if we make it to the last card, we will predict that that's the special card. So in this case, it's kind of obvious that that's what you would do. With one card and you know it's special, you're just always going to predict that that's special and you're always going to win. Okay. So then there's the assumption. So assume true for an n-1 card deck. So assume that no matter what strategy you use on an n-1 card deck, your probability is 1 over n-1. And then you have the induction step, which is to prove it's true for an n card deck. And how do we do that? Well, the way we're going to do that is we're going to think of how we can break the n card deck. So an n card deck is equal to one card plus a 50 or I'm sorry, one card followed by an n-1 card deck. So we can say, well, let's just see what happens on the first card. So on the first card, I can either predict, there's only two strategies that I can apply on the first card. It's either predict that it's special or predict that it's not. And then once I get to the second card, I have an n-1 card deck left, and I've already assumed that if I'm in that state, that the conditional probability is going to be 1 over n-1. That's the induction assumption, right? So for an n card deck, so let's write this out. For an n card deck, let A1 be the event. That we assert that the first card is special. Let S1 be the event that that the first card is special. Okay. So. Okay. Okay. So then what we're going to do is we're going to say, okay, first assertion can either be A1 or A1 complement. So the first assertion could be A1. If it's A1, then we're saying that the first card is special. And we're going to win only in the event that the first card actually is special. First card's special with probability 1 over n, right? Probability that any given card is special is 1 over n. Okay. So probably 1 over n, we win. And then with probability n minus 1 over n, we end up in condition S1 complement. And we're going to lose in that case. Or we can assert that the first card is not special. With probability 1 over n, it will be special and we'll lose. And then with probability n minus 1 over n, it will not be special. And then we'll be left in the case of a 2 of an n minus 1 card game, which we know by the induction assumption, we win with probability 1 over n minus 1. This is the assumption. So then let's think about it. Okay, what's the probability we win? Given that we assert that the first card is special, it's equal to 1 over n. Right? We only win if the first card is special. It's very simple. What's the probability we win? Given that we assert that the first card is not special. If the first card's not special, the only way we can win is, right, so this is our winning path here. And in this case, the only winning path is here, followed by here. Right? So it's the probability that we win, given that the first card is not special, times the probability that the first card is not special. Right? This is just the multiplication rule. Probability that we win, given that the first card is not special, 1 over n minus 1 by assumption. Probability that the first card is not special, n minus 1 over n. We get cancellation for 1 over n. So it's 1 over n, and we've exhausted the two cases, regardless of what our first assertion is. And so we've proven the claim. So at first, a claim that seems pretty general. We can simplify it by breaking into cases, doing induction, and using what we know. So that's an example showing how we can apply the various concepts that we've built up in this class regarding conditional probability using induction to answer that question.